like to introduce our next speaker, Rob Izzard from the University of Surrey. And
hear me okay?
Yeah, I've got a, yeah, I can see a pretty screen now.
That's how it looks out of my window.
In your dreams. Rob is going to talk to us about stellar pathways. I was going to say something about giant killers and Arsenal beating Newcastle the other day, but
I wasn't going to mention that.
No,
I was in a coma in the first half, so.
Right. Okay. Well, Rob, tell us something about stellar pathways.
Good morning, everybody, and greetings from a very sunny location above the clouds. It's not underneath, sadly, but that's how it is. So I was asked to talk to you about stellar pathways. It's a very vague title, deliberately chosen by the people running the school, I'm sure. So I've taken a bit of leeway. I'm really going to talk to you about physics today. So to give you an idea, I'm going to start off by saying what the sun does. And I'm going to approach this from the point of view that you've never studied stars in much detail before. So those of you who know this stuff at the beginning will get to stuff for you later on. You can go get a coffee and come back. Everybody else, actually, it's quite interesting. So, and then I will extend that to stars of other mass. And I should say before I start that other people will speak about stars of other mass today and later in the week. So please follow their talks as well. Then I'll talk a little bit about binary stars, because that's something that I work on that has been completely ignored for most of my career, which is great. It means more jobs for us. So there's a lot of unique channels and stellar pathways that haven't really been explored. And I'll talk a little bit about population synthesis, which is the link between our stellar modeling and how we link to things like the Gaia dataset that you just saw. So let's get going. I hate putting equations into talks, but you're all PhD candidates. So I think that means that you can handle some basic equations. Stellar structure is something that it's one of the older parts of quantitative astrophysics. Stars have been studied for thousands of years, of course, and in terms of with calculus in the last couple of hundred years. And there's some basic principles that apply to how we calculate structure of stars. And I'm not going to go into the great detail of this. I just want you to be aware that the equations that we solve when we calculate stellar structures on the computer are very simple. They are simply mass conservation, energy conservation, the standard things that you know from everyday life. Hydrostatic equilibrium is the same equation that you can use to study atmospheres on Earth or around planets or things like that. It's exactly the same. Energy transport is probably the most difficult. That's how you get the photons from the center of your star to the surface and then when they're lost. And there are several ways to do that, but I think it's reasonably well understood. I should say that these equations that we solve, you can get structures of stars very straightforwardly. There's no explicit time evolution in that, and we'll get to that in a minute. I've put a book recommendation here. I'm well aware this is a school. If you want to learn a very nice introductory course on stellar structure, then Prialnik's book is excellent for that. It's not particularly advanced, but I think for most people, that's absolutely fine. And it would do you well to have at least a quick look. And I should say there are many other books out there, of course. So the evolutionary part of what happens with stars is, it depends on this luminosity equation here. And I'm hoping you can see my pointer. This DL related to dN, where epsilon is this nuclear burning rate in a star. Now, of course, this is how stars evolve. Stars are essentially big fuel tanks filled with hydrogen. For example, the sun is born with 70% hydrogen. It's mostly hydrogen. And that's whatever was left over from the Big Bang, mixed with a little bit of material from other past exploding stars and things like that. And what keeps the stars from just collapsing is that they ignite nuclear fuels in their core, and they go through a series of nuclear burning cycles. And you've probably seen some of these before. The most common is combining protons to make helium, and indeed that is the most efficient in terms of making energy. But there are many other cycles as well. You've got the triple alpha, which is 3 heliums to carbon. You can then capture alpha onto carbon to make oxygen. Oxygen then captures an alpha particle to make neon. Neon then goes to magnesium, and so on, until you get to iron 56. Now, the reason for that is that iron 56 is the most stable of the nuclei. And so what will happen, well, the most stable of the nuclei made in stars, commonly, that is. And you can't add any more protons or alpha to that and get energy out. It becomes endothermic, and of course that doesn't help support your star. So the question is really, in stellar evolution, which of these cycles happen and what happens when the fuel runs out, which is absolutely key. So let's have a look at the sun and the pathway of the sun. Okay, so this is the evolution of the sun. And I've made some stellar models of the sun, and this is a picture of it, of course, very accurate color. And you see, we've got age on the x-axis here, and we've got the log of the luminosity on the y-axis, and that's in solar units. You've got to get used to solar units. So 0 is the sun now. And you see, if we put 0 across, we get to about 4.5 billion years for the age of the sun, which is, we know from other evidence as well, for example, radioactivity on Earth, that this is pretty much the age of the sun now. So there's the sun now, there's the sun at birth. It was a bit dimmer and it's getting warmer. This is not why global warming is happening, just in case you worry about that. It's very slow. But what happens is that you can see that most of the life of the sun, the luminosity is around what it is now. And we call that the main sequence. And in that time, the sun goes from a central hydrogen of about 70% to eventually around 0. So the sun actually uses up all of the fuel at its core. Note that the X generally means the abundance of hydrogen, and C here means central. So it's the central abundance of hydrogen in the star. And the star changes a little bit during that time, but not a huge amount. Now we can plot some internal features of the sun, and we can show how it evolves in terms of its core properties. So here I've plotted on the x-axis the density of the sun, and I've plotted on the y-axis the central temperature of the sun. And the main sequence is actually this small region here. And the sun starts here and it evolves up and to the right. And so as it loses access to fuel in the center, that is, it starts to burn the hydrogen, the center actually becomes more compact. And this is log of central density. The central density goes up by a factor of 10 during the main sequence, but the central temperature doesn't change very much. And that's typical of stars. They tend to be thermostats. And the reason for this is because the nuclear burning rate depends on the temperature very, very sensitively, like T to the power of 10 or 20 or something like that. So that acts as a thermostat. If you squeeze the star, you have a little bit more burning, which makes the star expand and cool again. So they're some of the best thermostats in the universe. Now, I should say we can also follow the evolution of the star as it goes on, right up to the helium ignition line, and we'll talk about that in a minute. If we look at here, for example, the nuclear burning rate, which is this color bar here, so yellow is strong nuclear burning. You see, actually, the sun has most nuclear burning in the core, but a lot of the envelope still has some nuclear burning all the way through the main sequence. It's not particularly fast up here near the surface, and this is what's called a Kippenhahn diagram. You'll see these quite a lot in stellar evolution papers. You have time on the x-axis and the mass coordinate on the y-axis. So these are like slices through the star at different times. And you can plot any property you want, and I'll show some more. But this is the nuclear burning. And you see that the structure of the star is actually pretty much the same all the way through the main sequence. I hesitate to say that it's a boring phase of evolution, but it's not the most exciting in terms of things really changing. We can also plot the hydrogen abundance in the star. And you see, as the star gets older, the central hydrogen abundance drops. So the red is 70% and 0 is down at the bottom here in sort of purpley blue. You see the central abundance does drop and it exhausts hydrogen around 7, 8, 9, depending on how you want to define it. It never quite goes to 0 until about here. It exhausts hydrogen in the core. And of course, that's why the star, or in this case, the sun, gets a bit hotter, is because it's adapting to the fact that it no longer has this hydrogen in the core. Now, what happens when this hydrogen runs out? Well, you can see here, around 10 gig years, around here, hydrogen's completely gone in the core. So what happens then? Well, you have what's called the transition to the giant branch. Now, you saw this in the Gaia talk. Stars, they become very large when they run out of fuel. And this is the transition from central burning of hydrogen to a shell burning of hydrogen. And then you go on to further burning cycles of helium and so on. And in the sun, we predict currently that we think there'll be a first giant branch and then a second one, which is called the asymptotic. I'll get to why that is in a bit. If we zoom in on the timescales for that, you see that actually the timescales for these are extremely short. Remember, the main sequence is 10 billion years, while core helium burning is far less. Red giant branch is just a spike in this kind of diagram. And yet these stars are the brightest stars that we see. They're the ones you'll see in the sky when you look at them. So the stars very quickly go through phases like this. And what's going on here? Well, if I plot another Kippenhahn diagram and I zoom in on the time at the end of the main sequence, you see what's happening. And again, this is the nuclear burning rate. What's happening is you're transitioning from on the left here, you've got a, not constant, I mean, it's a log scale, so it's not constant, but it's a pretty smooth nuclear burning profile throughout the star, up until you reach the giant branch over here on the right, where you've transitioned from real core burning into a shell here. You see the spike in the burning rate in a shell. And what happens is during that phase is that the star expands and it becomes a red giant. The core contracts because it runs out of fuel. Remember, it wants to stay hot, but it can't. It heats up until it ignites in the shell around the core. And then you end up with a very compact core with a bright shell and a huge star. So the fuel exhausts, and this is something you can remember in general for stellar evolution. When the fuel exhausts, you switch to shell burning. And when you have shell burning, you have big, bright stars for a very short time. They don't live in that phase for very long. Now, what happens to the sun after it has hydrogen shell burning, and then it ignites helium in the core? The reason for this is that as you have the shell burning going on, the core gets bigger and bigger in mass. And so it becomes more and more compact as well, because the gravity, when you have more mass, it becomes more compact in such a core. Eventually it gets hot enough in there to ignite helium. And when that ignites, you have a helium burning phase, and then you run out of helium in the core. And then you go on to what's called the asymptotic giant branch. I'll show you why it's asymptotic in a minute. But the end of the life of the sun is that there is mass loss during this asymptotic giant phase. So the sun, it never gets to a stage in its evolution where it's hot enough to ignite anything beyond helium burning. It doesn't go on to make iron, for example, and it loses all of its mass in what we would call a planetary nebula, something like this one here. This is the Cat's Eye Nebula, which is very beautiful. And then all you're left with, you've flung off all of the layers of the star, which were hydrogen, and you're left with just the carbon oxygen, what are the remnants of helium burning, which is a white dwarf in the center. And the white dwarf starts very hot and bright, and then it drops in luminosity very fast. It's just like dropping something very, very hot into space, which is very cold. So it cools, it radiates and cools. Okay, so that's the basic evolution of the sun. I'm hoping there's not too many surprises there. The last thing we need to do to construct the diagrams that we need to study stellar channels is to look at what happens to the radius. Well, the radius is approximately a straightforward function of the luminosity. They're related by this equation, which is black body equation. You can find that in any basic quantum mechanics textbook. The sun is, to a very good approximation, as are most stars, a black body. So the radius spikes twice on each giant branch, just like the luminosity does. Now, what we tend to do then is to plot the effective temperature, which is this temperature here. That's the temperature at the surface of the sun were it a black body, which is very close to the actual temperature. We plot that as a function on the x-axis with the luminosity on the y-axis, and we end up with a diagram like this. And you saw these very briefly in George's talk. This is what's called a Hertzsprung-Russell diagram. This is a luminosity versus effective temperature diagram. Note that both are logged, so we always log scale these. Also, the effective temperature is backwards. So blue is on the left. I mean, this is 10 to the 5 Kelvin down here. That's pretty hot. And red is on the right. So 1000 Kelvin is somewhere in this color bar here. And this shows the evolutionary track of the sun. It is born at this point here. It evolves up here somewhere, back down, up here, and then it becomes a post-AGB star when it loses all this material in its planetary nebula phase. And then down here, it becomes a white dwarf. Now, I've labeled all of these things with colors here, which are all the different stellar types. So you'll see the main sequence are in orange, the giant branches are in red, the helium burning is in blue, and the white dwarfs are these horrible pastel colors because, well, we don't care about them so much at this point. So let's zoom in on that part where the sun is, and I'll show you all of the different parts of the channel that it forms in the Hertzsprung-Russell diagram. So the star starts down here at helium ignition. This is where the big cloud that formed the sun collapses and starts to ignite ignite hydrogen, not helium. I'm going mad this morning. And this is the main sequence burning here, this orange bit. And this is most of the life of the sun. So this is 9 billion years of the sun will be sat just here. It doesn't change much. What happens then is it exhausts its hydrogen fuel in the core, and it transitions into this giant structure here. So it evolves up the giant branch. And it keeps going up there until it reaches this point where helium ignites. Now, you'll hear terms like helium flash when you go to talks or when you read papers. The reason that it's called a helium flash ignition is because the core is degenerate. And so it tends to be that when you ignite it, it does not expand to compensate for this ignition. And the density stays high, the temperature stays high, so the ignition runs away. And you have a very, very violent ignition of helium at that point. But it's not violent enough to break up the star. So the star then settles into this core helium burning phase, which the observers would call the red clump. And then eventually it starts to burn helium and hydrogen in shells. And that's what this asymptotic giant branch is here. And again, it's not burning in the core, it's burning in shells at that point, which is why the star stays as a very large red giant. And you can see why it's called asymptotic. It's not quite in the same position as the original giant branch, which goes all the way up to the ignition here. However, it is asymptotic to it. They're like two asymptotic lines. And it's not a very exciting name. I'm sorry about that, but you will see this in the literature quite often. When the mass loss kicks in, the star then moves off and becomes very blue. So the planetary nebula is way off to the left, 10 to the 5 Kelvin. And that happens very quickly. So there is no real, if you look at this kind of diagram, there's no time scales involved in this diagram. So I wanted to plot you a nice diagram to show you the time scales for each phase of evolution. We have here exactly the same plot for as we showed before. Instead of luminosity on the y-axis, I've got the stellar type, as we just described. The main sequence where it's hydrogen burning is all the way out here to 10 gigayears. And then you have the next phases, which come up here. So you've got the giant branch here, this transition zone in the Hertzsprung gap here, and then the giant branch. And these are extremely short compared to the main sequence. Even shorter then is the helium burning and asymptotic giant branch, which here looks, you can't even distinguish it on here. Now, what this means is that if you look at a population of stars that are like the sun, then you won't see very many of the asymptotic giant branch stars. They are very bright, but they're very rare. And then once it's a CO white dwarf, it does nothing for the rest of its life. Now, that's just the sun. So that gives you a very quick overview of stellar evolution. We can actually look at the mass as being the main parameter of a star. So the sun has a mass of 1 solar mass. And this is the solar mass symbol here. You see the little round circle with the dot in the middle. If you've never seen that before, that's the symbol for the sun. Now, low mass stars, less than about 0.9 solar masses, tend not to do anything in the lifetime that they have. And the reason for that is that they are still on the main sequence. Even if they were born at the beginning of the universe, they are still on the main sequence. So they've expanded a little bit, but that's it. Haven't done anything particularly exciting. Stars less than about 8 solar masses, they tend to be able to ignite helium, so like the sun, but that's it. After that, they have a lot of mass loss on the AGB, which means that they then become white dwarfs. However, stars that are high mass, that's 8 solar masses or above, can go all the way up to silicon burning because their core is hot enough that they can do this. And then they'll make an iron core and explode as a supernova. Now, I'm aware we have a couple of other talks on supernovae and massive stars, so I'm going to leave this to them to study this in detail. But the mass is the key parameter when you're looking at different evolutionary channels. So when we look at the mass, we have to look at this thing called the initial mass function. And this is, you can plot it very easily. This is just the number of stars as a function of mass. So if you want to look at a population in a galaxy like Gaia, this is what you need. And you see low mass stars, 0.1 to 1 solar mass, very common, lots of them. So this is just the probability per unit mass on the x-axis. So it's, again, log scaled. So you see there's a lot more of these. And the massive stars are very rare. So most of the stars that you see in the universe actually are just red dwarfs. They don't really do anything. Kind of dull. These low mass stars that are less than 2.5 solar masses, we distinguish these mostly because they have a red clump here rather than a blue. They don't go very blue. These are the evolutionary tracks of these stars in the Hertzsprung-Russell diagram. So this is 1 to 2.3 in this case. You see they zoom up here to the giant branch, and these points are from models. That's why they're a bit messy here. But these stars will be very rare. So you can see the main sequence is a well-defined band here, and the red giant branch where it gets very bright is also a very well-defined band, just like you see in those Gaia plots. If we go to the more massive stars, these can have bluer helium-burning phases here, which is an interesting feature of those. But otherwise, they're pretty much the same evolution. There's no massive difference, at least qualitatively. A little brighter. You see the main sequence extends to brighter, so it's 1,000 solar luminosities at 8 solar masses. That's quite bright. Now, when you get to more massive stars, 8 to 20 solar masses, these again are quite interesting, but they again move over. They don't really have a particularly well-defined giant branch as such, but they do have this phase at the end of their evolution, which is where they form a red supergiant. So stars of these masses will have a red supergiant phase, but then they explode in a supernova. So they're interesting objects in that regard. If you go even more massive, and here we're doing more than 20 solar masses, so this is up to 10 to the 5 solar luminosities, very bright. They jump straight across the Hertzsprung-Russell diagram. You'll see there's no red supergiant phase. They explode as supernovae, probably while they're helium burning in, have an equivalent to helium burning in the core. They really never make the shell burning phase. They never have time to form the shell. But what they can do, which is interesting, is they can have a lot of mass loss in this phase, which makes them much like the planetary nebulae have. They zoom across here, they're still helium burning stars, and they form what are called Wolf-Rayet stars. So around 10 to the 5 Kelvin and 10 to the 5 solar luminosities. Very bright, lots of mass loss, very interesting objects. And some of the brightest stars in the sky are in fact in this region here. And these are helium burning stars. You haven't seen the green ones yet. That's because they're very rare and only happen in very massive single stars. So these are what we call Wolf-Rayet stars. That's a definition based on spectra. Now, we can combine all of that data and we can zoom out. And this is sort of what we call a theoretical Hertzsprung-Russell diagram. And if we zoom out, you can see these tracks, which are the transition between the giant branch and the white dwarfs. So the white dwarfs are this pastel colored track down here. We have two types of white dwarfs, carbon oxygen, oxygen neon. They're slightly different. The oxygen neon is slightly more massive, but otherwise they're just the same. They're born here, and then there's no more nuclear burning, and they zoom down here. You should note I've also got some neutron stars down here, which are green, I think, because they were green in Doctor Who, so that makes sense. Those also start hot, and then they just get dimmer as life goes on. So now let's do a slightly different plot, which is the pathways as a function of mass. And I think if you're going to get anything from this talk, this is what you need to learn. That the mass is on the y-axis here, and the age is on the x-axis. So what you can here trace the evolution of every star that is born. And for example, a 0.2 solar mass star is born down here, and it does nothing except stay on the main sequence for its lifetime. That's fine. If you look at a 10 solar mass star, it stays on the main sequence, does a little bit of helium burning, and then becomes a neutron star. That's fine. No, I'm ignoring the later burning phases because they're very, very quick in this diagram. You wouldn't see them in this diagram. But the things to note here are that the mass is key to telling us what pathway the star chooses and what are the what happens to its final remnants. So we've got the short helium burning here. The massive helium stars are up here. They can form black holes, for example. And the red giants are all down here. Now, if we go to this one, I can show you that what terminates the evolution of the star is of great importance, of course. So the more massive stars have winds, yes, but they end as supernovae. The lower mass stars, they move from left to right here. They just have wind mass loss. They don't have supernovae. So this is the kind of evolutionary diagram you would normally see if you read stellar evolution papers, for example. Now, that's assuming we know everything. We don't. This is probably a more accurate state-of-the-art view of stellar evolution. We don't really understand where these boundaries are. There may be some neutron stars up here at higher mass as well. This boundary here is definitely blurred. We're not at all sure where that is. There are lots of things that still need studying in this. Don't think that stellar evolution is a solved topic. It is not. But when you have this mass loss, which terminates the evolution of the star, think of it like this. You can think of the onion shell in the star. So the more massive stars have these different shells of burning in them, and the mass loss will strip consecutive shells off the surface. So low mass stars, you'll strip off the hydrogen, bit of the helium, and you get left with the CO. The massive stars, you can strip the hydrogen, the helium, and there might be some of these left, the carbon, neon, and so on in the bottom. And it all depends on how much mass you've got to see which cycles you can ignite. Now, the other main parameter in stellar evolution is the metallicity. This is the content of the star that is not hydrogen or helium. Just a brief word on this, because everything I've said so far is for solar metallicity. Metallicity is not fixed. Many stars have different metallicities to the sun. But if you have a lower metallicity, what it tends to do is to shift your mass boundaries down because the star is hotter. And it also tends to reduce mass loss, which helps to do that. And also the stars have shorter lives. So all of these sequences move to the left in this diagram if you do that. And that's because the star is hotter, so it burns faster. Live fast, die young. It's very true. So. Now, very quickly, binary stars. These are stars that are gravitationally bound in orbits. Much like the Earth goes around the sun, you have one star going around another star. And if you've ever studied orbital theory, you could probably study Kepler's laws. All you need to know really for the purpose of this talk is that the period increases when the separation increases. You can calculate the period and the separation. These are the key variables that you need to know whether stars interact. And of course, periods are very easy to see from spectroscopy, which is great. So we can observe those quite simply. And why are these important? Well, if you take two stars like we have on the right here, the left one is just a normal main sequence star, doesn't do anything, but the right one is more massive. That one, much like me, I guess, as stars get old, they get bigger, and especially in lockdown, doesn't help. And this star will then get bigger and bigger and bigger until it expands to reach this point here, which is where the gravitational balance of the two stars is equal. And so the material here is not formally bound to either star, and it can flow over and fill what's called the Roche lobe. That's this equipotential surface here. And then you can fill them both. And that allows you to transfer mass to the secondary star. You can spin it up. You can also have them fill these and then eject the whole envelope surrounding the two stars. This is called common envelope evolution. So such systems will leave you with very peculiar stars that you can't get otherwise. And they're very interesting objects. And these, of course, cannot occur in single star evolution. Now, how many stars are in binaries? Should we actually care? Well, if you're looking just at the sun, you could look at the data from Duquesnoy, Mayo, or Raghavan's papers from 2010. That's all great. This is as a function of spectral type. Now, I'm a theorist. I don't work as a function of spectral type. So I've translated this diagram into the one below, and I've used Mo and DeStefano's newer paper, which is fantastic. Now we have the fraction of systems that are single, binary, triple, quadruple, so on, as a function of initial mass. And you see, if you're looking at low mass stars, so 0.1 is on the left corner here, 0.1 solar mass stars are, 90% single. But as soon as you get to the sun, you're starting to have 30% or so are in binaries, maybe 10% in triples and quadruples. And when you get to massive stars, up here is around 40 solar masses, you've only got 10% single stars. So if you look at massive stars, which are the important stars for making supernovae and hence all of the chemical elements in the galaxy, then you need to deal with binary evolution. Otherwise, you cannot possibly get any of your predictions right, and your stellar models will be wrong. And we found that a few years ago, there was a paper by Ugsana which looked at the period distribution. So remember, the period squared is proportional to the separation. a separation cube, so you can convert. So short period means very close stars, and if stars are close, they will interact. And the solar-like distribution of periods, so this is log period in days. The solar-like distribution is this red curve here. This is low mass stars. You see most of them have very long periods. They're 10 to the 4, 10 to the 6 days. They are so far apart that the interaction is negligible. They're only gravitationally bound, but otherwise they act like single stars. So you can model stars, populations of the sun quite easily. The problem with massive stars is that the curve is completely different. So the SANA results show that the distribution of periods in stars that are around 20 solar masses and above is actually peaked towards the very close systems, which means many more of them will interact. And so we did a population study of this, and we found that if you look at the massive stars, only actually 29% of them are effectively single. That includes the wide binaries and the single stars. 3/4 of them have some kind of interaction, be that mergers, be that stripping of envelopes, common envelope evolution, all kinds of stuff. And so to get the statistics right, to actually understand these systems, you have to understand how binaries work. And in this plot in the bottom left, I've put some complicated stuff, triples and quadruples. I won't mention them more, but triples and quadruples tend to be what we call hierarchical, which means a triple is actually a single star, effectively, in a wide orbit around a binary, or a binary in a wide orbit around a single star, depending on how you define it. Now, so effectively, the binary physics is what you need to understand, and then you can put them in wide orbits around them. If they are in closer orbits, they tend to have chaotic orbits, which means they don't survive. So they can't possibly live to make the channels that we're interested in when we look at stellar populations. And similarly, quadruples tend to be a binary in a binary. So we have some binary specific channels, carbon-oxygen white dwarf mergers. To get two white dwarfs so close together that they can merge, remember they're the size of the Earth, is impossible inside red giants, because red giant stars are so big. So the red giants have to spiral in towards each other in some complicated way. And if they can merge, they make type 1a supernovae. You can strip red giants to make helium stars, which are called SDB and SDO stars. These are studied a lot in AMAR, for example. You can strip massive stars to make Wolf-Rayet stars. I mentioned that already, but these can then explode as type 1b and type 1c supernovae. And if they are in very close binaries, they can explode as long gamma ray bursts, because you've got a lot of angular momentum in the binary as well. You can also merge stars to make what are called blue stragglers, and also red stragglers if you merge them when they're giants. What this does is to mix a companion star into the core of your existing star, providing more fuel. So your star suddenly looks very youthful. It becomes bluer relative to its parent population, and it just looks like a younger, more massive star. We see many of these, so we know they exist. In binaries, you also have novae, which are stars that suddenly go very bright, but then return back to their original state. These can be thermonuclear in nature, where you ignite hydrogen that's accreted on the surface. They can also be what are called classical novae, where you have brightness coming from disks accreted around one of the stars. Again, the physics is quite complicated. I'm not going to go into much detail, but they're very interesting objects, and again, historically very well known. And finally, the merging neutron stars and black holes, these must come from systems that are binaries or triples or quadruples. They have been observed as gravitational wave sources. You can also observe merging neutron stars as kilonovae, for example, and I'm sure we have talks on that later in the week. So, but these all come from binaries. These channels are very specific to binaries. Now, how do we go about linking the observations to our models of binaries to understand all of the physics that's going on? And this is the bit that's maybe a little more interesting and a little less background. So we want to quantitatively link the models to observations. And to do this, we need, say, birth functions. I've already showed you the initial mass function of stars. So that's how many stars are born with particular mass. The problem with binaries is that you also then need to know what is the period distribution, and you need to know the eccentricities of the orbits, and you need to know what is the secondary mass distribution, and so on. So the binary parameter space is huge compared to single stars. It makes it much more complicated. You then also need to know a star formation history in your galaxy that you're simulating. Okay, that's fine. You also need to know the metallicity history in theory as well, if whatever you're looking at changes with metallicity. And then you need stellar evolution models to predict what will actually happen to your stars. You need both single and binary. But what you can then do is to predict the number and the properties of the stars in the different channels of which you're interested. And you can compare this to the observed number. And the reason you do this is for several reasons. You want to understand the parameters in your models, because your models all have parameters. And you maybe want to rule in and rule out different models of evolution because you don't really understand how things work. And that's basically what we do in science. So we want to quantitatively understand what's going on in these stars. And the simplest way to do this is to just calculate the number of stars. So if I want to say, how many main sequence stars are there in the stars I'm looking at? That's pretty straightforward. You need a star formation rate. Fine. You need to get that from some kind of galaxy model. Okay. You need the probability functions. We get those by observing stars in the solar neighborhood, so that we observe stars such as low mass stars or main sequence stars, especially to see what their birth probabilities look like. So how many stars have long periods, how many have short periods, that kind of thing. And then in your model, you need a selection function. What this means is you have to select stars that you want. So if you're looking at main sequence stars, that's easy. When the star's a main sequence star, you make that function 1. And when it's not a main sequence star, you make it 0. It's a delta function, essentially. And then you have a final part here, which is the part that requires a lot of calculation. How long does it spend in that channel? So if you have more stars in the main sequence, this is probably because they spend longer in the main sequence. I mean, obviously, if you have more and spend longer, then the count goes up. Now, this is quite a complicated thing because you have to sum it over all stars and all time to calculate the number of stars you'll see in the sky. You can simplify this somewhat. If you assume the star formation rate is constant, then you can cancel out this term in this expression, and that makes it far simpler. But you can cancel it out by taking the ratio of two types of stars. So here I have N1 over N2. It's the ratio. So if you take, say, the ratio of the number of red giants to the number of main sequence stars, that's just a much simpler calculation to do because the star formation rate disappears if you assume it's constant. And in the galaxy, it's constant within a factor 2 over the last 10 gigayears or so. So it's not that bad, given all the other uncertainties are quite large. You still need to know the probability functions. You still need your selection function. You still need to know your time in the channel. So I've put those in these sums here. And the cost is a computational cost then in calculating these sums over the whole parameter space. So that's all of your different initial masses, periods, things like that. So you do really need a fast stellar evolution code if you're going to do this. But we can make predictions. For example, this is a prediction of the number of type 1a supernovae as a function of time from a galactic population. The observations are these points here, and the different models are these curves here. The details are not important, but you can see we have here 3 different models for different channels of 1a supernovae. The pinky one doesn't really fit. The red one probably fits. If you add it up to the blue one, maybe they both happen. It's possible. But this is just to show that you can actually quantitatively can now compare these kind of distributions to the observations. We can also predict many different channels of things like where does chemistry in the universe come from. This is a plot I put together yesterday for you. It's the mass loss rate of carbon-12 from a population of stars. So if you want to study galactic chemical evolution, these are the kind of things that you will need. You need to know at what rate does your population of stars pollute all of the galaxy around it. And here you see we have many, many different channels for where does carbon-12 come from. We have a lot coming from Wolf-Rayet stars, from AGB stars. We have very little coming from novae, but there's some there. All these different channels, and sometimes sometimes they're important, and sometimes you care. So we can also make predictions about Gaia, for example. We can say, well, this is a Gaia Hertzsprung-Russell diagram. You saw some of these in George's talk. Well, here I've made a prediction of what is the observed binary fraction. If we look at Gaia data, what should we see for the binary fraction? And you see exactly what she sees. You see a main sequence, which is this dark band going up here. You see above it the binaries, which is what she showed. In here, you have the low mass main sequence stars with white dwarfs. You have white dwarf tracks in the bottom left corner down here. And you have red giant branches going off to the top right. Now, the reason that a lot of these look single is because to have a red giant in a binary, you need to have a very long period system. And to observe a long period system, you need to have Gaia up there for a long time. It hasn't been up there for very long. It's only a few years. So these actually would be observed as single stars. And this is pretty much what we see. So now,
need to be wrapping up.
I'm aware that this should be my last slide. Unfortunately, it is. How did I manage that? I got a couple of links here for you to try. The first one is a link to the binary C code that I wrote. You can try that online and you can make your own stellar channels. You can try anything you like. You can put in any types of, any masses, any separations, everything. Please go and play with that and you'll get some evolutionary sequences like on the right here where you see the Roche lobes and you can see whether they overflow and form different types of star. Please do give it a go. Don't all 100 of you do it at once because you'll crash the server, but it's not my server, so that might be quite fun. But I've also put a link to my window to the stars code. You could try that if you want to run some single stars very, very easily. It's a piece of software. There's a virtual machine there. You can just download it and run it, and you can immediately run your own models. I use this for science as well as for outreach, as well as for teaching. So it's a very useful tool, and I recommend you go and have a look at those. So I'm done.
Okay.
Amazing.
Thank you very much. Thank you very much, Rob. We've got a couple of minutes for questions. We've got
I can't see them.
one online.
My chat window's disappeared. Hang on, I'm going to stop there. There we go. It's returned now. There we go.
Right. So Heather's asking, what does spinning up the secondary star involve?
Okay, so when you transfer mass, you also transfer angular momentum. And when material accretes onto a star, it will spin it up. And it turns out that under broad approximations, you can only accrete 10% of the mass of a star to spin it all the way up to the point where the material is unbound on the surface. So stars can be spun up very, very easily. I'm not sure what you mean by involve. I mean, then for some stars, this spin up may be enough to change their evolution. If the star is particularly young, doesn't have any serious chemical gradients in it, so if it's a young main sequence star where the chemical gradients are very shallow because it hasn't had much nuclear burning, then the star can actually be spun up to the point where it can have extra mixing because of the rotation. And that may then turn it into a helium star later on. And so those are very interesting because they may be a channel for making Wolf-Rayet stars, maybe for black hole mergers as well.
Right. We've got a couple of questions on metallicity. Dan Cornwall asks about mass loss. What drives mass loss in Wolf-Rayet stars? And why does it depend on metallicity? If you could answer that one very quickly.
I think there's a talk on this, isn't there, coming up?
I think there's going to be something on that.
Yeah, I think it's best left to them to answer that. What drives the mass loss? They're very, very bright.
And given that we're pretty well bang on 11 o'clock and we've got quite a lot of other things to get through this morning, I'm going to, if you can, Rob, if there's any other questions online, you can.
I can deal with some of them online.
Do typing, that'd be great. So thanks very much. We'll be hearing again from Rob later this afternoon when he's going to be telling us a bit more about the skills that we need to be scientists, or some of them. So thanks, Rob.